Okay, I want to talk now about Ampere's law. It's a close relation to Gauss's law. And to understand that, we need to understand magnetic flux. Magnetic flux, which is phi sub B. Okay, and you remember we talked about phi sub E before. Magnetic flux would be the flow of magnetic field lines, B field lines, going through a surface. If we think of a 3D surface and we think of a magnet being in there, and we think of the field lines, and I could draw more of them, but you get the sense anything that comes out comes back in. So the magnetic flux through a closed surface, through a Gaussian surface or a closed three-dimensional surface, has to equal 0. Whatever goes out comes back in at some point. And the reason for that is that there are no magnetic monopoles. Right? Because we never have a situation, here's my Gaussian surface, where I just have a south or a north. They don't exist. If you break a magnet, you get two magnets. Weaker magnets, but still magnets. So another way of saying this is the magnetic flux through a closed surface of B dot dA is 0, meaning there are no magnetic monopoles. And that's one of Maxwell's equations. Maxwell's equations. And if you know Gauss's law, you already know one of Maxwell's equations. Ampere's law ends up being very similar, and it's the third Maxwell equation. Actually, I don't know what their numbers are, but it's the third that we'll learn about. And Ampere's law goes like this. Remember Gauss's law, we had that three-dimensional business here, and you've got some kind of charge in here, Q enclosed, and we related the E field is related to the charge enclosed divided by epsilon 0. Well, Ampere comes along and he said, we already know that we can't use that same formulation for magnets because there are no magnetic monopoles. The net magnetic flux is always going to be 0. But what he said was that the integral of B dot ds ends up being equal to mu 0 I. What that means is if we have a current I, and I'll call this I enclosed, you have I penetrating, I enclosed, I through, something like that. If this is my I, if I have a circle around this, if I actually have any kind of shape around it, and this is just 2D, okay, then the magnetic field integrated with ds all the way around there is going to equal mu 0 times the I through the middle. Okay, so if this is I1 and this is I2, we don't care about this one. We only care about the one that's penetrating, that's going through the center there. And that's my I enclosed. In other words, if you can't see it, if this pencil is the current and this is a closed loop, then B dot ds, the integral of B dot ds around that whole thing equals mu 0 times the current that's going through it. Doesn't matter where it is. Whatever current is going through the middle of that ends up being equal to the integral of B dot ds. This makes it really easy to prove the magnetic field around a current-carrying wire. And let's do that right now. Okay, here's my current-carrying wire. And I know the integral of B dot ds around that whole loop. Again, I'm going around a whole loop, not over a three-dimensional area there. is going to equal to mu 0 I enclosed. Here's my I. And if I want to find the magnetic field at this point P, a distance r away, then all I want to do is I want to draw a circle symmetric around I with a radius r. Okay, the integral of B dot ds anywhere around there, since it's uniformly distant from that current, that B is going to be a constant. So I can just rewrite it like this. Mu 0 I enclosed. My I enclosed is just I. Well, ds, integral of ds around that whole loop, surface integral, the line integral all the way around that whole loop is just going to be 2 pi r. It's going to be the length of that whole thing. So you end up with B times 2 pi r equals mu 0 I. Slide that up. So that ends up being very simplifiable, if that's a word. Mu 0 I over 2 pi r. And that's the equation that we found way long ago for the magnetic field from a current carrying wire. But it's additionally the one we verified by using the Biot-Savart law. So this ends up being a very powerful means of finding magnetic fields. If we do this now, let me get a new paper. If we do this now for a coaxial cable, and let me shade this in. That's one current carrying surface right there, and this is another current carrying surface there. Okay, and let's say this is thin. Let's say this is just a radius, uniform radius R2, and it has a current I2, put it like that. This has a radius R1, and again, I'm not worried about the difference between here and here. We're just going to assume it's a thin cable. And this has a current I1 in the opposite direction. I don't even know how to draw that. About I1 in the opposite direction. This looks an awful lot like Gauss's law. So what we want to do is we want to find out what the magnitude of the magnetic field would be outside and inside here. And we'll just start with that. There's more we can do. So let's write Ampere's law. Integral of B dot ds equals mu 0 times I. So first of all, outside both. Integral of B dot ds, I'm going to draw my Amperian loop. Oh, I like that term. Amperian loop around there. And I'm going to draw it so it's, don't lose my video. I'm going to draw it so it's outside there and it's uniformly centered on there. And so outside both, what you end up with is integral of B dot ds equals mu 0. And the current, what we're going to do is going to be the difference between those currents. I'm not going to worry about direction right now. I'll just call it I1 minus I2. Okay, here's my Amperian loop. The current enclosed is going to be I1 in this direction minus I2 in that direction. So we have that. The B field is uniform because I've chosen it symmetrically. B times the integral of ds is just going to be, again, 2 pi r equals mu 0 I1 minus I2. Then we divide and we get B equals mu 0 I1 minus I2 over 2 pi r. Okay, that's outside both of them. That seems pretty easy, doesn't it? Okay, now let's go inside. Inside, oh, between, I should say. Between. What you have here, slide up there, between the two of them, you've got that still, I'm going to draw my Amperian loop in here now. Okay, and so I'm going to have integral of b dot ds equals mu 0 I. This isn't too hard. Now once again, we only care about the I enclosed. So I don't care about this whole thing. Doesn't this look a lot like Gauss's law, where the stuff outside doesn't affect the E field? Stuff out here doesn't affect the B field inside. So what we have, take the B out, because again I've drawn it symmetrically. B integral of ds equals mu 0, and in this case it's going to be I1. Well, integral of ds around an entire circle is 2 pi r. That ends up being mu 0 I1. B equals mu 0 I1 over 2 pi r. So Ampere's law, not that hard. Next time I'll talk about Ampere's law in the context of a solenoid.